Hello and welcome to a video on sketching polar curves. This has come after a request. I know it's very likely to come up in your next paper as well. There's bound to be something on polar. I don't know if it's going to be sketching, I really don't, but let's face it, it's not uncommon for them to ask you to sketch polar curves. And yeah, it can be difficult. Now, word of warning I first wanted to say, I'm using, well, first thing I want to say is if you want to get good at this, try all sorts of functions, like just with a little bit of trig in there, adding a constant or something like that. Try and sketch them yourself first for a given range, and then just compare it to the output on something like GeoGebra. But there is an important warning here. You will find that GeoGebra or Desmos or whatever, I think the Desmos is the same anyway. Somebody tell me in the comments if Desmos is different. But we only sketch curves when R is positive, yeah? R must be positive. Because it represents a distance, and that's not necessarily the way software or maths handles it. They don't, it's perfectly okay to say, well, R could be negative, and then you're going in the opposite direction to where the angle is, and that's basically how it works if you allow for negative R values. But Edexcel doesn't do that. Edexcel is very clear in the book that they don't do that, and so if you do compare your final graph to some output on GeoGebra, bear in mind that something like cos 4 theta, if you had r equals cos 4 theta, you should get only 4 petals there. But when you draw it on GeoGebra, here's r equals 4 cos theta, you get 8 petals basically, because it ends up drawing for negative r values. And so you get these 4 as well. But yeah, it's watch out for that. That's all I'm going to say. Anyway, let's practice it. Let's not do r equals cos 4 theta because I think they're well covered in the book. Let's do a few different ones. I was going to start with an easy one though. R equals 1 plus cos 2 theta. Now r can't be negative here just because this fluctuates between -1 and 1. So that's kind of nice. You don't have to worry about that. Standard approach, I'm afraid. There's no easy way of doing this. It's table of values. It really is. Don't think there's some kind of shortcut. Maybe if you find a Cartesian, something like that. I've very rarely seen cases where bothering to find a Cartesian actually helps you sketch it, because polar curves are really interesting, and quite often you don't recognise the Cartesian form immediately as that's the lemniscate or something like that. It's much easier just doing the table of values. I just don't think there's an easier way. Anyway, there are certain tricks you can use though. You might start by doing, something like this if you're sketching this one. Okay, theta is 0, cos of 0 is 1, 1 plus 1 is 2. Pick quite fine values at first, unless it starts seeming like a waste of time. But I'm going to go for pi over 6. You get 3 over 2 out of that, because that's going to be cos of pi over 3, which is cos 60, which is the same as sine 30, so it's a half. 1 plus a half is 3 over 2. If you did pi over 3, though, suddenly you're going to get cos 2 pi over 3. All of a sudden that's negative, and that's going to go to 1 minus a half, which is minus a half, because cos 2 pi over 3 is the same as cos of... let me just get this right. Cos of it's negative. I can just see it in my head basically, and I think that's the right number anyway. But I'm wondering myself now, because cos of pi over 3 is a half. Cos of that's the same distance from pi over 3 to 2 pi over 3 over here. Basically, the middle of pi over 3 and 2 pi over 3 is going to be 1.5 pi over 3, which is pi over 2. In other words, that's at 0, and so it's got an equal distance, and so that's minus a half, and that's a half. Anyway, you've got a calculator, so why am I even bothering, worrying about this? So we get a half there, run the values through. There'll be more of me umming and ahhing about different signs of trig values in a minute. But I've actually worked this one out anyway, all the way through. The thing is, you can immediately see that once you're going to get up to pi here, you're going to have gone through the whole range of values of cos, and it's just going to repeat. And so that's like advantageous to you when you do the table. I'm just going up in increments of pi over 6 here, and like I say, I'll just go up to pi because that's all I really need to do. And you've also got this beautiful symmetry that it goes down and then up, and then I'm just going to say for the next few values it repeats. Yeah, and so I reckon I've got enough to draw it now. Now remember, this is not x and, these aren't x and y here. They stand for the, where you're looking, in other words, like your viewpoint is theta, pi over 3, pi over 6, pi over 2, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and pi, yeah? It's your viewpoint from the origin, and r is how far you have to go from that origin to reach, where your point is. It's turn basically and walk. Okay, so initially turn nowhere but walk 2. So we're going to start at 2, then turn pi over 6 but walk 1.5. That's going to be like down there. Then turn pi over 3 but walk a half. Well, that's even closer, so that's probably going to be about there. But then by the time you're facing this way, you're back to 0, so it's coming round like that. Yeah. And then at 2 pi over 3, we are, yeah, it's come round like that. Okay, at 2 pi over 3, we're at a half again. So there should be like symmetry between this one and this one. It should be the same distance anyway from there to there. And then 3 over 2, a lot of symmetry going on here. And then at 2, so it's going to go like that. And then it's just going to repeat once you get to, you know, like the next one, which would be like 7 pi over 6 if you like. Well, that's going to be exactly the same as what we were back here. It's just going to scroll through again just because of the way the cos, you know, I've worked out because I know cos 2 theta looks like that. Yeah, y equals cos 2 theta, cos 2x. Yeah, it's just a squash. So after, you know, you complete the whole period. And so, yeah, it's just going to repeat like that. And so it's going to be the same underneath. And the same underneath there. Oh. Okay, so that's a nice one. You're probably thinking, yeah, I can do those ones. Good. Okay. Well, if you can do that one, you can do any of them. If you can be careful doing it. The problem is people get bored of doing this, so they start skipping it, and then they make mistakes. That's what really happens. Or that's how I feel anyway. And so I've got used to just doing it the tough way. Okay, so root 3 plus tan theta. Now, the question I grabbed this from originally said minus pi over 3 up to pi over 4. Yeah, it was from the A-level maths, revision maths questions by topic website. Good website, and it had these, you know, they're all from old OCR papers, and they'd only asked you to do it for this range, which is much easier. I'll tell you what, should we make it harder and say let's just do the whole thing from 0 to 2 pi, because it will bring up all sorts of issues. And if we're doing from 0 to 2 pi, we're going all the way round, looking all the way around and plotting points. Look at it like that. Look at it going all the way around and walking out. Okay, so first thing I want to do is I want to think, well, okay, let's say I started from like where they suggested. Let's go from minus pi over 3. Let's show that we can do their question initially. But then I'm going to stretch the graph out and we'll do the rest. So if we were doing this, we would have something like this. At minus pi over 3, well, that's where you're going to get r is 0, isn't it? Because tan of pi over 3 is tan of 60, so that's root 3. But tan of minus pi over 3 is minus tan of pi over 3, so that is going to be root 3 minus root 3, which is 0. So there we go. I then thought, well, okay, I know it's going to be the same pretty much going from here to here. Well, I mean, if you want to take one between a third and 0, why not take a quarter? Yeah, and there you're going to get root 3 take away 1. Yeah, which is still still positive. Okay, so that's not a problem. Okay, when we get to 0, tan of 0 is 0, so you get root 3. When we get to like pi over 4, I'm not doing it in even increments here because I'm just worried about really the sign and whether it's changing into negative at all. Tan of pi over 4 is 1, so that's root 3 plus 1, and then by the time you get to I could go on from here basically, but let's just quickly do the question as if it was the original question as I found it. Okay, so we're at 0 when we're looking out there. Yeah, I'm actually going to draw dotted lines because the original question, we'll do this one in a second, I promise, was just minus pi over 3 up to pi over 4. That was supposed to be minus pi over 3, but it doesn't really look like it. Let me just try it a little bit better. Accuracy is really helpful for these. And that's another reason why people go wrong. They're just not quite neat enough for it. Okay, so at minus pi over 4, a quarter's less than, between, minus a quarter is between 0 and minus a third. So, yeah, so once again, I've drawn this line. Let's draw it accurate. 60 degrees under, Nichols. Come on. I'm trying. Okay, so it's going to be something like that. Up to pi over 4 like that from the original question. Okay, you're at 0, but then at minus pi over 4 you're at root 3 minus 1, so you're like here. And then at 0 you're back at root 3. Remember, how far you're walking out is r. This is just where you're looking, if you like. Okay, and then pi over 4 root 3 plus 1. Well, that's root 3 is like 1.7, root 3 plus 1 is like 2.7, so it's probably like out here. So the original question's answer will look something like that. But let's keep going, because why not? It's fun. Let's change the question and learn, why this could be so problematic if they made it longer. Okay, so when you go up to like, tan of pi over 4 is 1, great. But what about like tan of pi over 3? Well, at tan of pi over 3, you're going to have root 3 plus root 3, so that's 2 root 3. So you're now at 3.4 when you get to like here, yeah? Okay, so we're carrying on. But then by the time you get to pi over 2, you got problems. Because tan of pi over 2 is infinite, yeah? And that is a problem. It's basically saying you need to keep on, when you get facing this direction, you need to keep on walking, keep on walking, keep on walking. You're not just not going to get there. So the curve's going to go up like that. Whoosh. Lovely. Okay, that's what's actually going to happen. I hope that makes sense. Now, let's draw the rest of the curve. Well, when you get to like from pi over 2 up to pi, think of the tan graph. It is really useful to think of the graphs as you're doing this. Because your asymptote is at pi over 2, and it's going to be from pi over 2 up to 3 pi over 2 is going to be your next period of tan, and it's going to be 0 at pi. From pi over 2 up to pi, in other words, when you're facing in this direction all the way up to this direction, round here, you're not going to have a value. It's undefined. The curve is undefined there. That's just the way it is, yeah? So that's the case when you're looking in those directions. So you're only going to have to start again at pi. Now, did I write what I write? Hang on a second. No, I did. No, yeah. Because the problem is we've got a root 3 plus. Yeah. So sorry, it's not just about when tan is negative. You've got to work out. I did actually work this out correct earlier, and I didn't seem to fumble on that bit. But yeah, you've got to work out exactly where we get to minus root 3 here. Well, we already know when we get to minus root 3, we already had it turn up. It was at minus pi over 3, and therefore this is going to be at 2 pi over 3. So the curve's going to start taking a value again at 2 pi over 3, which is like 120 degrees. So it's right there. And so it's going to now start taking a value. Okay, right, okay. Let's write that in. 2 pi over 3. Because finally we get back to r is 0, not r is negative. I hope I've worked that out correctly in my head as well. Tan of 2 pi over 3 is going to be the same as minus pi over 3, because you can take a pi. Yeah, absolutely. So yeah, we're going to get back to 0. So after this, we're going to start taking values again, because what about when you get to pi? Well, when you get to pi, tan of pi is 0, and so you're at root 3 again. Okay, so we are here, sorry. So it does take values here. It's going to come around like this. Yeah, it's got a lovely, I really like the shape of this curve. There's some beautiful symmetry to it. Okay, what do we have next? We have, oh yeah, and why am I drawing it out there? It's 0. It's so easy to mess up these questions, it really is. Like, so at pi, 2 pi over 3, it's at 0, and then it's going to come back out again, just like it did there, because it's going to have exactly the same values down here as we had down here, because of the periodicity of what we've got here. It's just going to repeat the same values. Basically, from there, and there, you're going to have exactly the same values, but that's 2 pi over 3 and 3 pi over 4 and pi. Apologies for the poor explanation there. But anyway, we carry on going as well, because from pi up to 3 pi over 2, okay, we're good until we get to 3 pi over 2. And we're going to have the same values once again here and here. So we'll call this like 5 pi over 4, and we'll call this, add a pi to that, 4 pi over 3. Yeah. And then pi. Pi is going to be our issue here. We're going to have exactly the same values. Key them into your calculator if you like. But when you get to tan of pi, sorry, I meant 3 pi over 2. Constantly messing it up. It's a bit late. I need to get some sleep, I think. But yeah, we're going to get infinite again, just like here we got infinite. And so what are we going to do there? Well, all that's happening, let's turn round with it. And remember, you've got to turn round with it. When you get to r equals, right, when we get to theta, yeah, we've done that bit. When we get to 5 pi over 4, we should be at root 3 plus 1. So actually plot it. When we get to 4 root 3, we're going to be at 2 pi. It should be exactly like this, but like, a rotational symmetry of it. And then finally, we're going to go whoosh, like that. And so you're going to get, I hope you can see it. I don't think it's a bad job. I'll show you the picture as it appears on GeoGebra, but I do want to say that some of it is not how Edexcel want to see it. This is the actual picture of it, but remember, firstly, it has this weird way of handling infinity on polar curves here. It's just giving you a it's drawing the asymptote, which is obviously wrong. That's so ignore the lines at 1 and -1. And also they're drawing the negative values of the curve there and there. Maybe I'll just quickly take a picture of it so I can actually show you what I mean. Annotate it. So yeah, bear in mind when you do these on something like GeoGebra, they'll draw the negative sides, and they'll also sometimes handle infinity in a strange way, not the way you should. So yeah, I'll just highlight what we actually drew. We drew whoosh and whoosh, and it is hard to do, it really is. But what we shouldn't draw, and I will point out, it's just because GeoGebra is drawing the negative values. Those negative values you shouldn't be drawing. Yeah, so don't worry about that. That is, we have done that correctly. Okay, so let's go on to the next one. I hope that shows you how to handle the cases where R is undefined. That's the main thing. When we get negative R values, that is a problem. But also when we get infinity. I think the one you asked about, Dylan, was R equals 1 plus sec theta. It's exactly the same kind of thing, really. We're going to have, okay, think about your values, think about your problem values, theta and R. Yeah. Now initially no problem because we're doing 1 plus and 1 over sec theta is 1 over cos theta, and cos theta is positive from 0 to pi over 2. So if we have like 0, pi over 6, pi over 3, pi over 2, that's not going to be a problem. And actually, like, because we've actually got the sec theta is actually, yeah, it's only when we'll talk about the negative case in a second. Okay, so what do we got here? Let's just do the positives first. Okay, so cos of 0, 1, 2, cos of pi over 6 is cos 30, so that's root 3 over 2, so 2 over root 3, so 1 plus 2 over root 3. And I only really want the decimal in many ways to plot it. That's cos of 60, which is a half, 1 plus 2, which is 3. And then pi over 2, cos of pi over 2 is 0. Oh, infinity. There we go. We've got our problem with infinity again. What's that going to do to the curve? So, well, let's start drawing it. Let's not do it all at the end, because we just turned through the first quadrant there. So we started off at 2, then we were at like a 1 plus a number, which, what is 1 plus 2 root 3? 2 over root 3. That's 1 plus 2 over 1.7. So it's basically 1 plus, it's slightly more than 2. Yeah, at pi over 6, slightly more than 2. It's going to probably look quite straight though. Yeah, that's the thing. That is going to look pretty straight. And then at pi over 3, we're at 6. Okay, well, that's 60 degrees, and we're at 3. Sorry, I don't know why I said 6 there. It's going to look something like that. Yeah. Now, it doesn't seem to be coming in that quickly though. It really doesn't. By the time you get to here, you're at infinity. So you've got to do something like, it's got to be going towards that because you're looking in that direction. It's getting further and further away. So that's why you'd have to show it like that. Oh, try to do a slightly better job. Ooh. Now, what about when it comes back down underneath? Well, you're going to be doing, let's think about the cos curve. Or you could think about the sec theta curve, which might be handy, but the cos curve is probably more well known. Okay, so between pi over 2 and 3 pi over 2, cos fluctuates between 0 and -1, which means that sec theta fluctuates between 1 over a number, which is between 0 and -1, and therefore sec theta is going to be between it's going to it's going to be like approaching negative infinity. Yeah. Let me put it like this. When it's here, we care about, yeah. If I can just draw the sec theta curve underneath, that'll probably be the easiest way. The sec theta curve just kisses it at -1 and then goes off to infinity there and there. Yeah. And so this is between -1 and infinity. Yeah. In other words, we're going to be doing 1 minus 1, or a number more negative than minus 1, and therefore r is going to be negative. So you can ignore the values between pi over 2 and 3 pi over 2. What it also means is you're looking and plotting in these directions. Don't worry about it. There isn't going to be anything on this side of the graph, yeah, which is kind of nice because we don't draw negative values of r. But GeoGebra does, yeah. Now, I'll show you at the end what it's doing in those ranges, because basically it is doing something. But yeah, we'll talk about that at the end. Okay, once we get to 3 pi over 2, we're all good, yeah. So almost put like, you know, like a break in your thing there. And at 3 pi over 2, basically it's going to repeat backwards, isn't it? It's going to go 3, and if we do like the mirror image points, what we're going to have like for pi over 3, 5 pi over 3, 5 pi over 6, and 2 pi. Okay, and it's just going to be, you know, backwards, like I say, 1 plus 2 over root 3. Let me get this right. Or have I put the 3 in the wrong place? Yeah, at 3 pi over 2, you are still at oh yeah, and aren't we going to get 0 somewhere here? If I labelled that infinity pi over 2 when it should be 0. Because of pi over 2 is... Oh no, that is infinity. That is infinity. It's right here at in between, isn't it? Pi. It will take a value of 0. So it will be at the origin, if you like, at pi, but you still would just plot that there, if you like. It would be a weird kind of point plotted just at the origin. And that, you know, technically would be included, I guess, under our definition. But, okay, it's not part of the continuous curve, though. So, right, yeah, I was just thinking about that. That's a random little point in there, which, you know, possibly, arguably, we should put on, because we didn't say we couldn't allow r values of 0. We said we could only allow positive, well, if you say only positive r values, then I suppose that gets rid of the having to put a point there. It's all on your definition. Anyway, this will get you the marks for Edexcel, I promise you. Okay, so we've then got at 3 pi over 2, you know, what was I worried about here? 3 pi over 2, what's because of 3 pi over 2 is some, yeah, it's still infinite, yeah. So that's where I've gone wrong. I was wondering why it wasn't going nice and symmetrical. That would be 3, that would be 1 plus 2 over root 3, and that will be 2. Good, I've got everything. So down here, it's going to be the same, very, very similar, but down there, and that's just because, you know, when you're at, you know, like I say, when you're at 5 pi over 3, you're matching with that one. When you're at 5 pi over 6, you're matching with this one. And when you're at 2 pi, you're matching here. And that's why it's going to go look like that. In other words, your final diagram should look something like this. That's all. That's what r equals 1 plus sec theta looks like. Now, draw it on GeoGebra. What does it show you? It shows you this. Now, what's these extra lines here? This is clearly what we drew, but what are these extra lines here? They represent when r is negative, yeah? They're just taking the negative r value, so rather than facing in, let's say we're down here, yeah, at this one. Rather than facing in this direction and walking what looks to be 3, in that direction, they walk it in the other direction at minus 3. That's exactly what they're doing there. That, by the way, is pi over 6 as well, I bet, isn't it? It was pi over 6 which was given 3, or pi over 3. So let me show you that. Okay, where's yeah, because these draw the circles. Yeah, pi over 3 at 3. And then back here on the negative, but we're doing 1 minus that, so it's going to be at minus 1. Yeah, yeah, because you've got a 1 plus on it, and so you're doing the 1 plus minus 2 rather than 1 plus 2. 1 plus minus 2 is at minus 1. But yeah, you're getting that image of this, if you see what I mean, and they're plotting those values. But ignore them, because you don't want them. You don't want negative r values. Okay, so I hope that's cleared up some of this issue with negative r values. I guess that's what you were worried about. It could have been, though, some of the other stuff like dimples, petals. Petals, to be honest, it's explained a lot by negative r values. Most of the petal confusion is about negative r values. Dimples, the conditions for a dimple, that is something, you know, which deserves its own video, and maybe I can do that if you're interested. But yeah, hope you found the video useful. I hope my waffling and my mistakes were forgivable, and yeah, carry on, keep up the good work. Bye bye.